One doesn't have to be a passionate fan of model trains to be fascinated by the way this steam engine looks. Hovering a few millimeters over the rails, it goes round and round without any friction and without any motor. On top of that, it really steams. But it's not water that evaporates inside the model steam engine, but liquid nitrogen, so cold that humidity condenses on it. The core of this magnetic levitation train is a superconducting material which conducts electric current without any resistance at temperatures below -183 degrees Celsius. In this state, it's able to trap magnetic fields. The resulting magnetic forces cause not only the levitation, but precision control above the rail, which is made of conventional magnetic material. An impressive experiment is designed to demonstrate how strong the forces are which hold the superconductor on the track. The superconductor is brought into a certain distance of a few millimeters above the magnetic rail and cooled down in this position using liquid nitrogen. Reaching the specific transition temperature of -183 degrees Celsius, the superconductor traps the magnetic flux of the outer field. Now we can remove the shim of a certain thickness which determines the distance. The superconductor has now memorized its position within the field of the rail. The superconductor is fixed at this distance and can only move along the magnetic rail even when turning upside down. But the effect lasts only as long as the superconducting state in the material is maintained. To set the superconducting levitation train in motion, one has only to give it an initial impulse by hand. Due to the lack of friction, the steam engine goes round and round until the liquid nitrogen is evaporated and the material warms up. Then the effect of superconductivity ceases, and what has been a strong magnet at low temperatures turns into a ceramic material without particular magnetic properties. Above the so-called transition temperature, superconductors are no longer affected by magnetic fields, and the locomotive drops back to the rail due to the effects of gravity. Then it's time to refill the liquid nitrogen in order to recool the superconductor below its transition temperature. During the cooling procedure, the superconductor is positioned within the magnetic field of the underlying rail. The distance between the locomotive and the rail can be varied by shims of different thickness, from 1/2 to 6 millimeters. Once the material has become superconducting, one has to apply quite a strong force to get it out of the magnetic field of the side track and bring it into the field of the rail. The magnetic field configuration of both tracks is the same, so the superconductor jumps to the distance which was fixed during the cooling procedure. To set the train in motion, it's enough to give it an initial impulse by hand. Granted, the model looks like a toy for playful physicists, but it could soon become reality for technicians. Of course, it remains questionable whether superconducting trains really will breeze along storefronts someday. However, some applications of this technique can already be envisaged, such as frictionless bearings or conveyance systems for clean rooms.